Can you hear me? You can hear me up there? Good. Okay. Yesterday I spent about $30 on chocolate bars, so we have lots of stuff for the next couple of days. Remind you about the exam that's coming up a week Friday. You've got to be reading in chapter 4, 5, and 6. And I put a little star around chapter 5 because it's got a bunch of continuous strategy space ideas which are we're not going to deal with for the test, but there's some ideas there. So just kind of skim that chapter, and you'll find some material in chapter 6 that combines sequential and simultaneous games a little bit, but also the test will cover a little bit of that material. Okay, I'll give you a more definite reply about that or information next Monday. Okay, but we will do a little bit of that chapter 6. Now, in the handout that I've put around, I've got an example of a game which I want to play for chocolate bars, and then after we have a look at that game, we're going to define some concepts. Then we're going to play another kind of game which is called a coordination game. But before I do that, I just want to step back and review this idea of the prisoner's dilemma. Actually, it turned out yesterday that when I put the handout up after class, and I went back, I did my little adjustments, and I pasted some things in, and I had a graphic for analyzing the two-person prisoner's dilemma game, the classic one, which was wrong. Okay, so what I'd like you to do is go and have a look in on that handout and see what's wrong with it. I did put a little correction to it, but not on that page. You have to click a link to get to it. But just trying to figure out what's wrong with that analysis of the classic prisoner's dilemma. That would make a good kind of exam question too. So let's have a look at the general idea behind the prisoner's dilemma. Okay, I mean, there's the classic story about prisoners, turning state's evidence on one another. But really, the key features have to do with the payoffs and kinds of strategies in this game. So in the simplest game, we've got two players. They got two things they can do, and in our little contributions game, we had them giving money to a charitable contribution or not, all or none. Some or out of an endowment. But the key feature of the prisoner's dilemma is that both players have dominant strategies. Okay, so or in a multiplayer game, that everybody has a dominant strategy, and we'll define that a little more strictly in about halfway through this lecture. Okay, but you got this intuitive idea that a dominant strategy is for a particular player is one that is best against everything that anybody else could do. Okay, so it's like, it makes sense if it's the best for you, no matter what the other players do, that you'll play it, okay? Because you can't find anything better to play for yourself, and other players would expect you to do that. Now, the second feature of the prisoner's dilemma is that if people didn't play their dominant strategies, they could all be better off. There's something in the game, whereas if they didn't do what would seem to be the sensible thing to do to play these dominant strategies, then they could all be better off. Now, what I did down here is I put a little stylized 2x2 game where often in the prisoner's dilemma idea is, could you get cooperative action where everybody could be better off, or would people in some sense cheat or defect on the cooperative outcome? And the way to think about and design kind of games where they've got this kind of structure is to start with some payoffs in any cell. But let's say that we start in the left-hand corner here where there's payoffs to A and payoffs to B. Okay. What we want is for there to be some other payoffs that are better for both than A and B. Now, here I put them A plus, B plus. Okay, so the plus is indicating both these payoffs here are higher in the preference orderings of A and B than in this cell here. So once we've got that idea, you say, okay, well, here's where kind of as a group they would like to be, or both of them would like to be here compared to this one. But if they're here, if they're both cooperating, then there's some temptation, okay? And the temptation is we want to have a higher payoff for the red player to defect against a cooperative action of the other guy, okay? So you can think of, if you're going to put a payoff number in this cell here, and again, on the exam, or just as you're thinking about trying to explain strategic interaction, say, what is this prisoner's dilemma? Why is it such a significant idea? Well, cooperation can be good for both, but if you try to do the cooperative thing, there's some temptation to do better for one player, given that the other player is cooperating, okay? And vice versa, if we look at the temptation from the blue player's standpoint, if the other guy, the red player, cooperates, the blue player can get B plus, okay, which is nice. It's better than his B, but he's not going to get B if he defects. He's going to get whatever this question mark is. So if that's a high number, okay, bigger than B plus, then there's that temptation to defect, okay? On the other hand, if you're both defecting and you decide to do the nice cooperative thing, we call that like a sucker payoff. You know, you're doing, I used to have this argument with my daughter when she was a teenager about recycling, and in those days it was really difficult to recycle. I mean, you know, you had to sort everything out, and I just said, well, look, if everybody else recycles, I'm better off. It's less costly for me not to recycle. Okay, and it's like, you know, and if I recycle and nobody else recycles, then I feel like a real dummy, and that's the sucker sort of payoff. Okay, so when you're thinking of these designing a prisoner's dilemma game or thinking about the idea, remember, you want to design a game where all players have dominant strategies, and to do that in a little 2x2 case, you know, we set the payoffs out like this. There's something that both could be better off, but once they're in that better off situation, each of them has an incentive to defect, given what the other player is going to do. Of course, given that they both defect at the same time, they actually go back here, but that isn't the reasoning. Okay, the reasoning is, if the other guy continues to cooperate as a blue player, I'm better defecting. The red player's reasoning, if the other guy cooperates, you know, I control my actions, I'm better off defecting. Okay. Now, we're both going to defect. I mean, we can both expect players to defect because those are dominant strategies. Okay. But the reasoning isn't along the diagonal, it's up and down the columns and across the rows. And this is this sort of idea of the reasoning is people's beliefs. Okay, we end up in the prisoner's dilemma here because people believe that, well, if they did cooperate, they'd get taken advantage of. Okay, so that's where you can think, well, gee, maybe we change the game to change those beliefs. And we'll see that when we do a repeated version of the prisoner's dilemma game, it's possible to actually get some cooperation because there's opportunities in a repeated game to punish people who cheat or defect, okay? But in the one-shot game, the logic is pretty clear, okay? Yes, you know the other guy's going to defect, but given he's going to defect, you better defect too, otherwise you're just a sucker. Okay, I'll put this up on the handout after class on the web if you want to print it off. It's just the logic of that two-person game. Now, whoops. On your handout, you have a game that comes from page 85 of the text. And what I like to do is play that game for some chocolate bars. What we'll do is we'll have the guys be the blue players. Okay, so males will be blue players, and females will be the red players. And I'm going to pick two people at random after we talk a little bit about the nature of this game to earn some chocolate bars. Now, if you look at the chart up there, you can see that you know, you might get this pair here where the ladies get 3 and the men get none. You might get the cell over here where the ladies get 9 and the men get 7, and all the other possibilities in between, okay? So what I want you to do is go through these 3 questions that we've asked, we keep on asking. What are you going to do in this game? And then, again, try and just sort of scratch it down. Remember, the guys, you're a red player, and ladies, you're ladies, you're a red player, and guys, you're a blue player. What are you going to do? But before you answer that, you might want to think about what's the other player going to do. Okay. And then, when you're trying to answer what the other player is going to do, you might ask, well, what are they going to be expecting what you're going to do? So try to go through that sort of logic, and then I'll just pick 2 people at random, and who knows, somebody is going to go away with perhaps a lot of chocolate bars, depending on the pairing up. So the idea here is you don't know who you're playing against, so it's kind of anonymous. Let's imagine that you're interested in more chocolate bars or less. Okay, so as a red player, you're interested in your red chocolate bar playoffs, and the blue player, you're interested in your blue chocolate bar playoffs. And what you want to think of is, what are you going to do? And before you think about that, or while you're thinking about that, you might want to think about, what do I think the other guy's going to do? Okay, and then to think about that, you might want to think, even deeper, which is, well, what are they going to do? They're going to be thinking something of what I'm going to do. I wonder what they're going to be thinking, what I'm going to do. Okay, so that you're going to choose a letter, and you say you're a guy. You're going to choose a letter, a blue letter, and I will choose a female from somewhere, and she will choose a red letter. We'll pair them off, and I've got lots of chocolate bars. $30 for the chocolate bar. You're not getting all those today, but somebody will pay off according to that table. Okay, so but I mean, the payoffs in the chocolate bars and the table are really to illustrate kind of a strategic point. And so at first, I just want you to think about this game. Okay, the numbers. I mean, trying to make them mean something in terms of there's a payoff here. Okay, so take a couple of minutes and. The answer isn't going to appear magically on the screen, so you might want to stare down at your own piece of paper and have a think now. Okay, what am I going to do? But you also want to think, what's the other guy going to do, so I can know what I should be doing. Okay. And of course, you'll be thinking the same thing, so I better think that through too. And then come up with a choice, and we'll talk a little bit about the reasoning behind your choices. Then we'll analyze the game. Yeah, you can talk to someone sitting behind you if you like. There's no need to have absolute stunning silence. We're not in an exam here or anything. Of course, it could be on the exam, in which case you have to be silent, but now you don't have to worry about that. You getting anywhere?
So we just choose one of these letters.
Yeah, you got to choose the blue one, but.
So you choose R, wouldn't you? Because it's got the greatest.
Okay, if you choose R.
It's got the greatest path for readers, so they're likely to choose.
Which one are they likely to choose? Okay, so if they choose that one. Okay, and so if they choose that one, and you choose that one, sorry, if they choose this one, what's your best shot?
If they choose L.
No, if they choose L, yeah, if they choose L, what's your best shot? Okay, so you wouldn't want to choose R if they choose L, even though that's their biggest number, and they might, if they focus on their biggest number, then they would choose L.
But no one goes first.
But if they choose L,
So no one goes first.
no one goes through. You're just trying to think about it in your head. What are they going to do? Okay, that's if they focus on their biggest number. But what is it they're going to focus in on? Okay. You guys getting anywhere?
Yeah.
What are you thinking?
I think this would be the best for both of us.
Okay, so you're gonna, as a male player, which one would you choose?
Will it be this one?
Remember, you only get to choose. You only get to choose one of these. One of the women is going to choose one of those, and it won't be the lady sitting next to you. Okay, so think about if you choose that one, what do you think the other player will choose? Well, remember, if you choose right, she would choose left there, right, to get her best. But if she chooses left, what should you do?
Oh, I'll definitely choose M.
Yeah. Okay. So that's you have to try and figure out what's your best response to what she's going to do, what's your best response. And remember, we all started from here. We could have started from somewhere else too. Okay. Did you get anything? Okay, so you think but you would choose B. Okay, what's your name? Abby. Abby, okay. Okay, so what'd you guys do?
We're tossing up, huh?
You're tossing up, eh?
Between M and R. We worked out all these ones are dominated. there's better options for a lot of people. So I reckon it's going to be one of these five.
I reckon they're going to go L.
Yeah, it's just
Okay, so what? Okay, given what you think, what would you choose? Given what you think they're going to do, just.
I think they're probably most likely to go for B, so I'm going to go for R. That's their sort of lowest risk, highest payoff.
Okay, but if they go for B, or sorry, if you go for R, what's their best choice?
So do they get to see what I've chosen?
No, but they're thinking about it.
If they go for R, their best choice is L.
Okay.
But
So if they
know that, I know that, then they're going to go for someone else.
okay, then what are they going to go for?
B.
No. If you okay, let's run this. What was your name again?
Isaac.
Isaac. Okay, so I'm talking with Isaac. Okay, and Isaac's trying to figure through. I'm sorry, I forgot your first name. Did I have it? Abby. Okay. Isaac's trying to think through a number of things. Like he's worked out some things he doesn't think are going to happen, but he's kind of hoping that they could go for this bottom cell down here where there's lots of chocolate bars, okay? But, so he's thinking if I choose right, thinking they're going to choose B, that's not really their best shot. If they also think that I'm going to choose right, okay? Their best shot is to go to L. And then, okay, so you think that through, and then you think, well, if they're going for L, then what's your best shot? You'd go M. Okay, so now you think if they go M, what's their best shot? To go L. And if they go L, your best shot is M. And if you go M, their best shot is L. And so to settle down, okay? So what are you going to choose? And what do you think they're going to do? Okay, so Isaac, after a little bit of inducement here, chooses M. But it turned out that Megan actually chose B. Okay. Abby, sorry. Abby chose B. So, Abby, what were you thinking? If you choose B, you could get 5 or 4 or 9, right? Yeah. But if you chose L, you could get 2 or 5 or 12. Okay, let's have a look at this. If red player chooses B, they got some pretty good payoffs here, 6, 5, and 7. That's pretty good for them, isn't it? So you're thinking, what's good for them, and then what's good for me? Now, out of the ones that are good for them, which is the best for them? R. R is the best for them because they get 7, okay? So you'd sort of think, well, if I was to think about B, and they were thinking like I was thinking, which is B is pretty good because I get 5, 4, 9, then I would expect them to be playing R if they think I'm going to play B, right? But if they play R, what can you do that's good for you? If they play R. Do you want to keep playing B if... You have to play the game. You can give them away, okay? Your nieces, nephews, whatever, right? Cousins. Okay, assuming you like 12 chocolate bars, though, but more than 9, then you go up to L, wouldn't you? So now, what I'm thinking is, at first you're thinking B looks pretty good. So you think, okay, B, and why is B pretty good? Well, it's got a basic number of chocolate bars. It's okay. It looks fairly safe. I could get better ones up here, but I could always get poorer ones. So that looks pretty good. If the other guy thinks that's looking pretty good for me, then they're going to play R. They got a specific best response. And then, okay, so if they play their best response, I shouldn't even think about playing B. I should be thinking about playing L. And if I play L, what will they think? If you're playing L, what's their best response? It would be M, because 4 is better than 3, okay? And then that reasoning process stops at M and L, and that's what we're going to call a Nash equilibrium. Okay, it's like any other pair of things you can think about, any other reasoning process you go through in this game. There's something about, if you think about it a little deeper, the other player won't be playing a best response to whatever it is that you think is going to happen in that game. Okay, so it's like you don't know what's going to happen. They can't see what you're going to do. You can't see what they're going to do. But so what we did here is we didn't get the Nash equilibrium. We got M and we got B, and it was partly, I mean, we'll go through Isaac's reasoning a little bit because he eliminated some other alternatives which weren't very good. Now that's another strategy you can take to this game, but if you just sort of stepping through the reasoning process, you could end up thinking, well, boy, the only place I can find it's kind of like fixed for both of us is, you know, if I believe L, then their best response is M, and if they believe M, if they're believing L, then the male's best response is M, and if the females are believing M, then their best response is L. And those are kind of mutually consistent, okay? Their actions and their beliefs. You know, you're going to be, as a red player, you're going to be playing what it is that the blue player expects you to play, because they're playing M on the basis that you would expect you to play L, okay? And you do actually play it. And vice versa, the red player is expecting the blue player to play M. That's why she's playing L. And lo and behold, the blue player actually does play M in that situation. But any other cell, you try that reasoning, is not going to work out. Okay, so we call that a Nash equilibrium, and I'll just so you don't have to have 12. Okay, you only have to have 4. But you can give them away if you don't want them all. Oh, sorry, are you getting 5? No, the guys get 5, ladies get 4. Because we're pairing off M and B, right? Okay. Okay, guys, fatten up. You can have one extra one for your friends. Okay, so let's have a look at this game. And it's different than the voluntary contribution mechanism game that we looked at, in that no player has what we call a dominant strategy. So let's have a look at this idea. And what we're going to do is look at this dominance process, and we'll come up with a definition of what dominance is. So let's sort of walk it through. When you're looking at this payoff matrix, you know, one thing you could do, or any kind of strategic situation, we said, if people have dominant strategies, they should play them. Well, let's see if the red player has a dominant strategy. And you start off, you just, you know, pick one. Okay, well, B looks pretty good, right? It's got a high number there. So if the blue player plays L, red player's B is the best they can do. 5 is better than 2, 4, 3, okay? But if the blue player plays M, then B isn't the best, L is the best. So B can't be a best response. Okay? What about L? Could L be if B can't be a dominant strategy, because B is good against L, but L is better than B against M. Okay? What about L? Could L be a dominant strategy? Well, no, because B is the best against L. As a matter of fact, H and T can't be dominant strategies because they're going to be worse than B against L. Okay, so this player hasn't got any dominant strategies. There's nothing that's best against anything the other player will do. It's sort of it depends argument. You know, if this guy did this, then I would do that. That's the idea. But what about the blue player? Well, does the blue player have a dominant strategy? We'll pick one that's looking pretty good. Let's take R. Unfortunately, R isn't as good as M against T, because 3 is bigger than 2. Okay. But R is pretty good against H, 4 better than 0. Okay. So neither M or R can be a dominant strategy, because each one is better than the other under some circumstances. That is, some strategies of the other player. So what about R? What about L? Could L be a dominant strategy? Well, no, because M beats it 3-1 against when red plays T. So again, it can't be a dominant strategy. So here's a game that doesn't have any dominant strategies. The prisoner's dilemma one is where everybody has a dominant strategy. In this game, nobody has a dominant strategy. However, the dominance reasoning actually can help you out here, because remember, the dominance idea is what's best against anything the other guy could do. That's a dominant strategy. Well, that's pretty strong because you got to be better than everything else that you can do against anything else the other guy can do. What if we just take things pairwise at a time and said, well, are some things bad, worse to play? And it turns out they are. Let's compare the rows H and B. So this is kind of in the direction that I was going, but a little bit different because you could eliminate H right away, okay? So H is dominated, ED, by B. B isn't a dominant strategy, but it's certainly better than H, no matter what the other guy does. Okay, because 5 is better than 4, 4 is better than 3, 9 is better than 6. Okay, so you sort of think, oh, okay, here's a game where I'm not sure what the other guy's going to do, but if I think about it, I can figure out something he wouldn't do. Okay, and why wouldn't they do it? Because if they chose to do H, they'd be getting an inferior choice against anything I do compared to choosing B. I mean, it's like, why would an intelligent person choose H? They can do better, Why? I mean, they don't know what I'm going to do, but it doesn't matter what I'm going to do. B is always better than H. Okay, so then it's another part of the strategic reasoning. Sometimes, okay, I can't find the best, but I can see things that are crazy to do. Okay, I mean, dominated. Now let's just cross that out. So I put a little bar through that. Now, this bar is in your head. Remember, you don't see these things. You're sort of thinking, oh, I don't expect the other player to play H. Therefore, I've got kind of a new game. Okay, this is like second stage. And you sort of think, well, the new game is just like the first game, except that now the red player really only has 3 strategies because I really don't expect him to play this one here. Okay, so let's see if we can carry on, and it turns out we can. Okay. Supposing we compare R and L for the blue player. Well, 1 is less than 2, 2 is less than 3, 6 is less than 7. Now notice we've crossed out H. See, L was better than R when we expected H to happen, but we don't expect H to happen now. So now we can eliminate L. In our heads, we can think, well, the blue player won't play L because the blue player would only play L if he expected me to play H, but we both figured out because we know the game that I'm not going to, as a red player, I'm not going to play H. It's going to be eliminated. So therefore, L will be dominated by R, not in a big game, but in this new game, the second round, which we call iterated, like we're going to go one step at a time. So let's eliminate L. Okay, so we can remember the idea is this is in your head. You're trying to cut out things that are bad. Well, L wasn't really bad all the time, but once you eliminated H, it is bad. Okay. Now, can we keep going? Well, yes, we can. We can eliminate T and B for the red player, and why is that? Because if we eliminate this column here, then look at 5 is bigger than 2, 5 is bigger than 4. 12 is better than 10, 12 is bigger than 9. So it's like, oh, okay, once we've eliminated the left column, the L column, then L does dominate the other alternatives. Okay, so we can eliminate those two. But it's kind of an iterated dominance, not as dominance in the full game. It's like as we boil this game down, then we eliminate some more options, and we find, oh, okay, if we're down to this little game here, it's really the red player is expected to play L. The blue player is expected to play either R or M, but M is better than R, so we can eliminate that, and we come up with what's called a solution to the game, a prediction of what will happen. We got close. We didn't get it exactly, but it's called iterated dominance. Okay, and the idea is that sequentially you're going to go through and you identify in a series of games, okay, little sort of connected games, and these are iterations in your head. So you really have to think this through. I mean, you got to be kind of sophisticated to, iterate all the way to the end. You might go 1 or 2 steps and trying to figure out what the other person will do, but we're assuming that you've got enough time to kind of work this out. And what we end up with is a pair of strategies, L and M, which kind of survive this process of iteration. And the payoffs that emerge are the payoffs from iterated dominance reasoning. Okay, so that's a game is called dominance solvable if it's either if you can use dominant strategy reasoning alone to kind of come up with an answer. And the idea here is that dominant strategy reasoning is pretty persuasive. I mean, dominant strategies dominated strategies are ones you shouldn't play, and dominant strategies are ones you should play. Okay, and if you can go through and identify dominated strategies, you eliminate them, then you kind of look at the new situation. You think, okay, it's I've got a new game going on here. Why is it? It's new in my head. It's new in their head. We know nobody's going to do this, so we got kind of a smaller game, and we just keep analyzing that. In this case, we're able to come to a solution at the end. Now, let me get rid of these little bars because I want to approach this a different way. And that's using the idea of best responses. Okay, now remember, these best responses are in our heads. We're not actually responding to actions that we can see, but we're trying to think, okay, I'm the red player. If the other guy did L, B is my best response. If the blue player, the column player does M, L is my best response. If the column player does R, L is my best response. So I put these little knots here. And you can think of this best response as a best response function. I mean, it's telling you what your best responses are as a player to every other strategy the other player could come up with in this game. Okay. Now we can do for the same for the blue player. Again, for the blue player, the best response function is going to look something like this. So I put these little X's in, and let's just reason through. Remember, the blue player is trying to figure out, what am I going to do, L, M, or R? I don't know. Well, if the other guy does T, my best response is M, because 3 is bigger than 2 and 1. If the other guy does H, my best response is L, because it gives me 5 rather than 0, 4. And you just go mechanically through. And what I'd kind of encourage you to do, just, once you figure out what the payoff numbers mean in a game, and you've written down the little payoff table, just mechanically go through and do the best response. If you do this with that modified voluntary contributions game with the threshold that I did yesterday, you'll have lots of X's and O's in your payoff matrix. Okay, and here we have one cell where there's a pair of best responses. Okay, that is what we call a Nash equilibrium. Now notice we got to the same point 2 different ways. One was using the dominance reasoning, just kind of going successively or iteratively, coming up with I can eliminate certain things. I can expect them to see that they'll be eliminated too. So we're all kind of at in the same page here, thinking about the game. And then we can eliminate some more dominated things, come up with a smaller game. Eventually we'll come to a solution. That's one way. The other way, which is actually a little bit easier, is to think about what's your best response. What's the other player's best response functions? That is, when you sit down and work them out and you find, oh, there's a pair of strategies here, L and M. Okay, a pair. Okay, Nash equilibrium is, the Nash equilibrium, or sometimes we'll just say equilibrium, drop the adjective Nash, because we're thinking of strategies. A Nash equilibrium is a pair of strategies, or in many player games, it's a whole list of strategies, okay? Now remember, when you're playing this game, you only get to choose your strategy. So what's the other members of the pair? Well, that's your beliefs about what the other guy's going to do. Okay, so the Nash equilibrium tells us for the red player what they're going to do and what they believe about what the blue player is going to do. And for the blue player, what they're going to do and what they believe about what the red player is going to do. And those beliefs are consistent. Okay? Everybody does what they're expected to do in the equilibrium. Okay? And we get these payoffs. Got that idea? Now, I put down some definitions on the handout for you of what a Nash equilibrium is. And just kind of let that idea sit in your head a little bit. I mean, don't think of equilibrium as an engineering concept. Think of it as a strategic concept. Okay? It has to do with what people are doing, their behavior, and it also has to do with their beliefs, what they believe. Okay? And so you're sort of sitting there thinking the Nash equilibrium really has to do with people's understanding of strategic interaction, what they believe other players are going to do, and what they're going to do themselves on the basis of their belief. Now, it has a particular characteristic in that people play best responses to what they believe, okay? And that's kind of a rationality idea, is that you've got some beliefs about what's going to happen, and you're not sure exactly what's going to happen, but here, they're saying, yeah, I am sure. I am, in this Nash equilibrium, as a red player, I am sure the other guy is going to play M, and my best response is L. and they're sure I'm going to play L, and their best response is M. And we can both work that out, so I can be quite sure that they'll be sure that to play their Nash equilibrium strategy. Okay, so once you focus in on a particular Nash equilibrium strategy, you see that is a set of beliefs and actions for each player. Okay, now, just want to, before we go to the next round of chocobars, I want to just talk about this idea of dominance. When we talk about one strategy dominating another strategy, okay, so we got a pair of strategies, and remember, you can look at it from the perspective of each player. You know, what we're saying is that no matter what the other guy does, this strategy, the first strategy is better than the second one. Now, that's intuitively that seems to make sense, and when you have the little payoff table, it's pretty easy to compare the numbers. But there is a couple of little subtleties you got to think of. One is that sometimes we talk about strict dominance, and sometimes we talk about weak dominance. And sometimes it's kind of slippery. You're not really sure whether a person is talking about strictly dominated or weakly dominated when you're working through an analysis. So, for example, compare the red S4 with the red S3. So these are two strategies, and the blue player strategies are A, B, C, D, and E. Okay? So you can see that S4 dominates S3 because 4 is bigger than 3, 2 is bigger than 1, 0 is bigger than -1, -2 is bigger than -3, 2 is in 1. So notice S4 for the red player, you know, it has a 4, that's pretty good, has a 2, has a 0, has a loss, has a 2. It's like the payoffs are all over the place, but the payoffs for the S3 are also all over the place. And for every one of the places you could be, S4 is better for the red player than S3. So that's what we mean by S4 dominating strictly S3. This S2 is the same as S3 except right here. Okay? And here, S2 has the same payoff if the other player, blue, plays C as S4 does. So it's like S4 is better than S2 here. It's better than S2 there, but it's the same as S2 there. It's not worse, it's the same. And it's better here because -2 is a bigger number than -3, and it's better there. Okay, so it's almost always better and it's never worse. Now we call that weakly dominance, and it turns out in some games the payoff structure will be such that people get the same payoff for a bunch of range of actions they can do. And so they're kind of indifferent between those, but in other situations, definitely one is better than the other. Okay, so we work with both ideas. If you're, again, you know, it's just a concept right now. The idea of dominance is a good idea, an interesting idea. If you have to work with it on an exam or on a table or in a problem, you sort of think, well, I'm working with weak dominance or strict dominance. Well, just be clear what you're doing, okay? Sometimes the weak dominance can lead you into some strange situations, which we'll see a little bit later on when we blend sequential and simultaneous games. But it's still an important idea, okay? A strategic idea. Now, the other table in here, which we're going to play for chocobars, is from a kind of a coordination game. And again, now that you've got this table, immediately when you see this table, you should, oh, I should run through the best response, okay? That's if you want to figure out what you're going to do, what's your best response to what the other player is going to do, and it working from the other player's standpoint, what's their best response to what you're going to do. So give that a try. Okay, mark the X's and O's. Just look at the table. I'm going to tell you what the numbers are and where they're coming from in a second. But just think if these are the strategies of the 0, 1, 2, 3, and 4 of the red player. Those are the strategies of the blue player. Got a pen? Because this table isn't in the book. So what are you thinking? Like if
So both players move at the same time.
yeah, it's the simultaneous game.
One of these, and the other player one of these.
Yeah, this is supposed to be blue and it's supposed to be red. But it's hard when you to get those colors. And the idea is to try to identify, like for the red player who can choose 4, 3, 2, or 1, 0, what's by putting a little X or O, be consistent. Then if the other guy plays 4, his best must be up there, right? Because 4 is better. Okay, so put a little knot or cross there. Put it. I can't remember what I did in mine, so it doesn't really matter, just as long as you're consistent with the rope. How are you guys doing? Okay, so do you understand what's going on? If you're the red player and the blue player plays 4, what's your highest number? Yeah, so that would be the best response. And if he does this one, 3. If he does that one, yeah, okay.
So am I trying to get the higher numbers, or is the red player trying to get the lower numbers?
Okay, the payoffs for us are almost always, the higher numbers are better, okay? And these labels are just for the strategy, so they're not payoffs. Okay, I'm going to tell you that in a second. If you just focus in on the table, then you can work out what the best responses are, okay? So let's, we haven't got any meaning. Always we want to figure out in a game what do the payout numbers mean, but even without that, you should be able to walk through and sort of say, well, what are the best responses in this table? And they're going to run down the diagonal like this. And let me just run through this reasoning, okay? It's like all we're trying to do is figure out from the red player's standpoint, what should I do? Okay, well, I don't know what to do because I don't know what the other guy is going to do. But I can sort of go, well, what if? Okay, what if the blue guy does 4? Then 4 is better than 3, is better than 2, is better than 1, is better than 0. So I should do strategy 4. If the other guy does 3, then 2 is worse than 3, and 3 is better than 2, is better than 1, is better than 0. So the best response is to do strategy 3. And so as you'll see on each diagonal, if the blue player plays 2, the red player's best response is 2. If the blue player plays 1, the red player's best response is 1. If the blue player plays 0, the red player's best response is 0. Okay, so that's where these little red knots come in like this. So that's a knot, and then we're going to put a cross by looking at blue's best response. So from blue's standpoint, in this game, whatever the numbers are, as long as higher numbers are better, I don't know what to do on the blue player. I got to make a choice. Well, let me figure out what the other guy might do. What if? Well, what if the red player plays 4? Then I can do 4, 3, 2, 1, or 0, getting 4, 3, 2, 1, or 0. I don't know. Okay, 4 that's the best given this payoff structure. Okay, if the other guy does 3, 3 is better than 2. 3 is better than 2, better than 1, better than 0. Now notice, as I go across the row, I'm concentrating on the blue guys, okay? Because I'm looking at it, trying to say, what's blue going to do? Blue is focusing in on blue's payoffs, not red's payoffs, but blue's payoffs, okay? And across each row in this game, there's a whole bunch of mutual best responses. And each one of those cells will be a Nash equilibrium in this game, okay? Now, let me go back and introduce you where these numbers come from, and then I think we'll have time to do one round of it, okay? So this is a game where imagine 2 people working together, okay? And when they work together, one person makes a part, another person makes another part. They put the parts together and they make a product and they sell it in the market, okay? And the idea here is that there's some payoffs that are going to come back to them from selling that product in the market based on their effort levels. But the output that goes into the market depends on both what they do, okay? So like if I put in a unit of effort and you put in a unit of effort, then we produce something and we can sell it. But if you slack off, then we haven't got anything to sell, okay? Or if I put in 2 units of effort and you put in 2 units of effort, then we got more to sell. But if you slack off a little bit, or I slack off a little bit, then we're going to have less to sell in the market, okay? Meanwhile, I'm putting in the effort. It's costing me. And so these little formulas at the bottom are just the the kind of reasoning process that's gone through to construct this sort of cell. It says, look, let's take it from the perspective of the red player. Your effort level of the blue player and effort level of the red player are going to be along this axis. So you can put in no effort as red player. The blue player can put in no effort, okay? So that's 0, okay? So nobody puts any effort. We don't get any output. Nobody gets any payment, but you haven't expended any effort, okay? So your payoffs are 0. Now let's supposing both of you put in 1 unit of effort. So we've got 1 unit of effort here, 1 unit of effort there. Well, you do 1 unit of effort, I do 1 unit of effort, we produce something, 1, and that, say it's valued at $2 for me, and you get $2 as well. Okay, so we sell it in the market. Your returns are $2 on the output, my returns are $2 on the output. On the other hand, it costs us something to put in our effort. Well, my effort is 1, but I get 2 back. Your effort is 1, you get 2 back. So the net payoffs are 1 and 1. Okay, got that idea? And same way, if you, moving up the diagonal is the same thing. Let's take this 4 and 4. Okay, you got 4 units of effort. I got 4 units of effort. The minimum is 4, so we're making 4 units of product, which we sell, and then I get 2 times 4 is 8. You get 2 times 4 is 8. But we've each put in 4 units of effort, and say effort costs us something, $1 each. So our net payoffs are 4 and 4. So these numbers are our net payoffs if we work together. But let's have a look and see what happens if I work really hard and you do nothing. Okay, so I'm the red player. I'm putting in 4 units of effort. You put in nothing. The minimum of 4 nothing is nothing. We don't get any output out, so we don't get any revenue, but it costs me 4 because I put in my effort. You haven't put any effort on the other hand, so you haven't earned anything, you haven't lost anything. So that's a -4 and 0. And every one of these cells comes from applying this kind of formula. And the idea here is that this is a game where it's different than the prisoner's dilemma game, okay? Because there aren't any dominant strategies. There are some nice payoffs for both of us, and there are some bad payoffs for both of us, even some worse ones up here like this. So for example, I might be thinking, like Abby was thinking here at the beginning, oh, look at B. B's got good payoffs for both of us if we do the right thing. But if you put in your 4 units of effort and the other guy doesn't put in their 4 units, I mean, if they expect you to put in 4, they should put in 4. That's their best response. But if they don't, okay, then you could get 2, 0, -2, or a big loss. Okay, so you're working for nothing. Okay, well, next class we'll come back and we'll play this kind of game for some chocolate bars. I want you to think about how are you going to play this game. This has got a little bit different uncertainty than the other games because we don't have these dominant strategies. It's like, what's the other guy going to do when I can't see what he's going to do?